Okay, good afternoon, everybody again. So welcome to the discussion session. And actually, Abhishek had the idea of having this like today. So yeah, but I think it's a good idea. And he asked me to moderate this session or agitate this session, whatever. And so this is Tasaki, and I'm going to chair this session. So I don't know how to proceed, but probably we'd better start with some definite questions and discuss about that. So I sort of listed some questions, and some of them are proposed by some of the participants, and some of them are written by myself. And let me, I think, start from this one. That is actually, this is continuation of Abhishek's questions to Marcos. So this is a quantum versus classical type question. So I mean, people are discussing all these foundation of statistical mechanics within the paradigm of classical mechanics for quite a long time. But now we are working mainly quantum. And the question is always raised, what is the difference between quantum and classical and how they compare? So let me start from this question that Abhishek raised. What is the classical analog of ETH? And I think Marco's answer was typicality. And I think Takahiro has a different answer, so why don't you? Yeah, louder, yeah.
I think you have to keep the mic really close and.
Okay, I think it's ergodic hypothesis.
Can you define ergodic hypothesis? Or what exactly do you mean? Ergodic hypothesis? Like,
yeah, microcanonical ensemble average equals the long time average. I think that is exactly implied by the ETH.
So it's just similar, but I would perhaps try to point out about the trajectories of a system through the configuration space. That has to be completely chaotic to have its correspondence with an eigenstate, which basically samples the energy window. Microcanonical energy window is something similar, like a given energy particle. It traverses the entire phase space, samples it enough so that if you average any local properties on that particular trajectory, the trajectory basically gives you a reasonable. So it's like a trajectory is like equivalent to kind of equivalent to an eigenstate, though of course they're not similar, but probably these are the two things. Like for example, the scars are considered to be some special trajectories which are periodic orbit, and the scars appears in the eigenstates which are actually mostly localized around those periodic orbits. So weird behavior of the eigenstate translates exceptional behaviors of the trajectories. So in that sense, perhaps ergodicity of single trajectories are somewhat correspondent to the ETH scenario.
Yeah, I basically agree, but do you have any? That's yeah. Yeah. We should sort of distribute the microphones. So where are the microphones? Yeah.
It's
yeah.
Oh, okay. Yeah, I guess eigenstates correspond to infinite time averages.
Yeah.
So you can translate any quantum statement to classical statement, but yeah, essence is set. So our infinite time average, which is classical stationary states, are described by energies. So that's the content of ETH.
So yeah, there was a question about it's not here, the present status of classical ergodic hypothesis. I mean, it's a notoriously difficult problem, isn't it? When Sinai proved the simplest case, people were sort of, I don't know, optimistic that it would be proved for materialistic cases. I think it didn't go that way. I don't know if it predicts the future of ETH or not. Is there any comments about the status of ergodicity hypothesis? Classical system? Peter, do you want to say something or?
That it seems to me not much has happened in the last decades. It is like a lost case.
Okay, so right, so there are basically no experts, I think. So okay, let's
Maybe
yeah.
can I add something?
Yeah.
Just something.
Use the microphone.
And now that is also an aspect of classical ETH. This A of E should slowly change with E, which is maybe not completely obvious in a very high dimensional space. I don't know. That would be for me the immediate counterpart of ETH.
Diagonal ETH.
I don't know.
Oh, I want to do this in a chaotic manner. So, so you know, you can come back to this question anytime you want. And does anybody want to say more? By the way, is video working? Oh, it is. Oh. Okay, ladies and gentlemen, let's go to the, yeah, and I don't know if there can be any discussion on this, but what is the classical analog of GGE? Is there any discussion on this? So in classical system, there are, of course, integrable systems with lots of conserved quantities. But is there any analog of GGE possible?
Oh, the answer is yes, and the definition is the particular degenerate limit of the infinite genus classical spectral curve. If this there's something, but so indeed, so we understand very well the structure of classical integrable systems, namely integrable PDE. So you can start with again in a finite volume, classify the entire spectrum of solution. It's essentially a nonlinear version of the Fourier transform, something like that. And then you have to identify the right thermodynamic scaling limit, and there are some mathematical structures. So it can be done, yeah. So I had 2 years ago in Brazil, I gave already a talk on that. Unfortunately, the paper is not out yet, so it's in my drawer, so hopefully it will appear.
But interestingly, they didn't know about GGE in the long history of classical statistical mechanics and integral systems.
Right, so what I'm saying, this is a new result that we will publish with my colleague, yeah. Because traditionally, yeah, people who work on these models, they are not really asking this type of questions. Yeah, they were not motivated by this kind of question. It is mostly pursuing these formal structures and so forth. But yeah, it can be done.
But is it, yeah, so is there any reason that people didn't realize that? Like, is it possible to realize in some sense, even theoretically, this GGE, classical GGE, starting with certain initial state? And
it's definitely something that it's worth exploring in the future, yeah. So theoretically, it can be defined, but then all these questions, which states do thermalize, which don't, and, you know, classes of initial conditions, smoothness, blah, blah, of course, many interesting questions.
Yeah, yeah.
I remember correctly, I talked to Emil Yuzbashan some time ago, this generalized microcanonical ensemble known for ages. If you take a classical integrable system and take long time average, it's equivalent to generalized microcanonical ensemble. Basically, you thermalize along each tori,
sure,
unless you have commensurate frequencies. Sure. And as this is, yeah, but if you have extensive integrals of motion, you automatically get GGE by standard arguments.
Oh, this was a good question.
Sorry, Anatoly, I disagree. I think if you consider a fixed classical integrable model, charges start rotating on the torus. This is a microcanonical answer. G should be something different. It should be particular weights. That means that you do not belong to a particular. You need to have a Wigner function which allows you to have probability being on different
Motion, why not? Have extensive state. If you look into subsystem size, it should be equivalent GGE to GGE as long as the integral is extensive.
I think there are two questions. The question of equivalence between GGE and generalized microcanonical ensemble.
Yes.
Those should be.
But in small systems, they're not equivalent. There is not even a question.
No. But if we have an extended system and we look at things locally, ensembles should be equivalent.
Yes.
I agree with that. I agree with that.
But
But if we just ask the question how to realize classically GGE, classically GGE is not the same as classical microcanonical.
if you have extensive integrals of
Because the variance of
no, but then quantum will also look into global quantities, you will never get GGE quantum. There is no way you can get exponential distribution. You will never get Gibbs distribution even in ergodic systems.
I have an impression we are discussing a slightly different question. You are discussing the question to thermalize to GGE. And I think we are discussing the question of just realizing the GGE classically as some probabilistic configuration. Begin with, you can just ask a question, can I have GGE to begin with as a state?
I don't think there is difference between quantum and classical.
Or
In extensive systems, but
So basically, I agree about this morally about your answer. The distinction disappears in the thermodynamic limit between GGE and microcanonical ensemble. But I don't disagree. I disagree with you from the point of view that this is just microcanonical ensemble, and it's just that, because once you have to take the limit of infinitely many degrees of freedom, and once you take this limit, your nice torus deforms and degenerates, and it's gone. So you have to regularize this limit in an appropriate sense, which is where the whole non-triviality lies. So this is why I said it's a particular type of degenerate scaling limit of the infinite genus classical spectral curve. And this is not just a microcanonical, it's not just a hypertorus on which motions are periodic or quasi-periodic.
So what is the situation about equivalence theorem? So of course, if the number of conserved quantity is finite, independent of the volume, then the equivalence theorem should be obvious. But if the number of conserved quantities grows with the volume, then I would say that the usual proof of the equivalence that you see in the textbook of David Rell say does not apply immediately. Anybody? Yeah.
That is in 2015. I have it here. It's in Annals of Physics, and the statement is in classical mechanics, we prove microcanonical version of the GGE by mapping blah, blah, blah. So it was not known. So he actually published a paper in 2016 about it. No. This is, I mean, he knows what the GGE is. So you have to look at the papers.
Okay.
So you just look at it. But I mean, he really knows about integrability. So.
Again, which paper?
So it says an Annals of Physics, generalized microcanonical of the Gibbs ensemble. So I can.
Or you can.
Right. Exactly.
Yeah, Marcos, you can write it on the board. Or
in the meantime, that's
right. Then we can continue to. Okay, so we had fun. So we go to the next. Well, the next question is, I think this is too vague a question, but I think we should keep on asking this question. So is there any essential differences between quantum and classical, especially when we are interested in thermalization? So especially we are working on quantum and sort of promising that we can do much more than people did in. Anatoly probably has a definite answer.
Well, I guess the only example, at least I know, which is still debated now, is MBL. That's where there was a difference between quantum and classical. But all other systems, I don't.
What is the
Many body localization. It's like
okay, but that's a phenomenon. But if you I'm now mainly focusing on the philosophical or sort of conceptual issue about thermalization. So when we are trying to understand thermalization or equilibration, is there any essential difference?
I mean, we know morally at finite temperatures, quantum and classical systems behave in the same way. It's kind of hard to expect that there is a huge difference.
But they are formulated in a very different ways. Yeah.
In classically, I mean, of course, the famous thermalization problem is the Fermi-Pastor-Ulam problem, where, for example, right now there are results such as like what is the equilibration time, and recently there's a result that this equilibration time increases with as you lower the energy density as 1/epsilon⁸ for the alpha Fermi-Pastor-Ulam. So in the quantum case, I don't think there are such. And also the way people study these problems are very different, and I don't think there are such explicit results. Right?
So you're saying that they're different. Do you think it's a fundamental difference or just a history study? One? Yes.
In the quantum thermalization, maybe entanglement is playing a major role. Does that something as whether in the classical systems we don't have an entanglement? Does it?
But correlation and entanglement are different. Entanglement, I believe, is a purely quantum mechanical. I mean, of course, correlation is there in classical physics. Entanglement, you think? Yeah, of course. That means that entanglement is not really important.
I don't know, because you could say that, I mean, it's philosophy at some point, right? But you could say that the reason that you get these topologically non-trivial ground states, that is because of long-range entanglement. So I think it is a perfect example of how quantum mechanics.
But ground states are quantum, we know that. You cannot get Fermi liquid classically, so ground states are quantum in general.
Are quite independent. One should not be confused. The thing is this: is the system is the topologically trivial state. It must have to be go to the quantum thermalization. There is no problem that the system should have to be the topological state of. It may be if the system topological state of matter go to the thermalization, there is no problem. But it's not that hard and fast that it must have to be.
But quantum, the topological phase is, I think, too much. Actually, I always personally think about this, and I don't know if this is meaningful, but of course, in classical case, if you have large degrees of freedom, of course, we do have irreversibility, and you can prove several statements. You can state several statements that says something is irreversible, but in classical case, I think you always must say that you sample initial state according to this measure, and then with probability 1, you see irreversibility. But I sort of believe that in quantum case, we are probably able to write down a single state without throwing any dice, and you just give a state, and you can say that this thermalizes. And
No, but quantum wave function corresponds to classical probability distribution by uncertainty principle.
okay.
So
Then,
comparing quantum state with one phase space point is just unfair.
okay, that's unfair comparison. Okay, but that, but you know, this means that, okay, is it really true? Because quantum mechanics is mechanics. Classical mechanics is also mechanics. And you know, classical mechanics plus measure theory is something else. So, okay, but this is an interesting point. Yeah. Yes?
Yeah, so that gives the correspondence back to set them in a fair footing, and then you see there is not much difference again.
Probably, can argue. Does anybody wants to say more?
Not existing.
Yep. But in many body quantum systems, not close to the ground state, usually don't see any energy gain. According to Marcos' philosophy, don't talk about ground state, and then not. Yeah.
Yes, to defend quantum system, the work I like was by Boris Fine, who looked into out-of-time order correlation functions, and then I think Tomasz Prazen had like rigorous work that those are like power law in quantum systems and exponential in classical systems. Don't know whether it's important or not, but this is definitely a distinction.
What is the, probably it's what's too.
This is basically echo, like out-of-time order correlation function, like it's what measures echo. And in generic quantum systems, local, I'm not talking about Lagen, those like the Roche's power law in time with local interactions. And classically, they're always exponential.
Can you write it? Is it possible to write down the reference for this? Yeah, probably we should do it because, you know, if we just hear, we just forget. And then you can take.
So, and this was introduced by Larkin Ovchinnikov, and now it's built. So, and essentially, if you think about, I don't know, say x and p as variables, it's almost like square of a Poisson bracket. And then if you have a chaotic dynamics, it should grow exponentially. Then various, well, there are experts in the room. Know much more. In large N theories, there are bounds on this exponential, even quantum systems are exponential. But then actually in 2000, I think 13, paper by Boris Fine, my knowledge, it's the first one, who studied it in spin chains, and they found that this grows as a power law. So physically, you might think about this as an echo. So you take some spin, propagate forward in time, perturb a little bit, propagate backward, and you see the difference. And in classical chaotic systems, it's exponential. That's like Lyapunov exponents and so on. Quantum, it's not exponential. The quantum systems are kind of more robust.
Then we can Google. Any other? And of course, then you can leave at any time if you feel like. So this is a very informal. Marcos, would you stay? Okay, so does anybody want to say more about this, quantum versus classical? And of course, you can raise a new question at any time.
What you said is like if in the classical, no, yeah, you just said, so in the classical case, if you start with a, instead of a point, if you start with a small blob, and if it's really, really tiny, I think you will eventually you'll see way quantum state produces.
Yeah, but you cannot say, you cannot pinpoint a single.
Right, you can't, but it has to be a tiny blob.
Yeah, that's means that means I thought that, you know, you cannot use only mechanics, but mechanics plus measure theory.
Right, yeah, but that shouldn't, I mean, like real systems are just one single.
Oh, okay. Yeah.
They're not a blob. So.
Yeah, but, you know. So if you, yeah, okay. But in real system, do we have probability distribution? No. No. Right. I don't think so. Because it was on a bad path which never thermalizes. So this is a problem about time evolution, not the observation. So even if the system is ergodic, classical system, even if the system is ergodic, you can always find a very bad initial condition starting from which you never thermalize. Even if you are unluckily on this bad initial state, however you coarse grain, you can never reach thermalization. Oh, so you're using measure. When you start saying typical initial state, you are using your measure theory.
You're saying there is a condition for the gas in this room that molecules will always stay in that corner?
Right.
You sure?
Yeah, it's a measure zero. So, but when you start saying that it's a measure zero, you can exclude. You are not only using mechanics, you are also using measure theory. And you are choosing your measure to talk about.
But is it proven that it's measure zero in many particle systems? Not just zero, it's really measure zero, right?
You mean you're asking me a question?
No, if you have this many particle systems, like classical systems, so are there initial conditions which don't thermalize? Like for billiards, we know a few particle systems, you have the scars, whatever, but if you consider, say, thermodynamic limit of classical spin chain or whatever, is it proven that there are conditions, classical conditions, which will never thermalize?
I don't know, but I thought there would be. I mean, you are very unlucky. I thought there is some. Anybody know? Of course, yeah. If you are in perfect, perfect square or perfect box, there are many. But I don't know. But it's like it's stronger than strong ETH. I don't believe that. But anyway, we can. Okay, so it's taking longer than. It's already 30 minutes. So can we go on like this? Okay. So there are, so as you see, finally, I have these very broad questions which could be very controversial or boring. And here are some concrete questions which may be very hard and lead us to nowhere. But this is a question from Sho Sugiura. So where are you? Oh yeah, can you say something about this question? Your motivation? Use microphone.
Theory of the gravel system. So if there's something analog of CAM theory, KM theory, what would we expect? So like what kind of ideas can we maybe or it might scale? Or it might be MBL system.
You should speak louder. So the question is there a quantum version of KAM, all right? And what is your guess, or what is your expectation? Richard, do you have anything to say? Yeah, Sho Sugiura. Yeah.
I would say that spectral perturbation theory is the natural analog of KM theory, right? Right? You just as KM says you that if you have two oscillators, right, and you made sure that the frequencies are not at resonance and the coupling is sufficiently weak, you will produce new. In some regions of phase space, the system remains integrable, and you have the KM tori. And just in the same way, if you couple two systems quantum mechanically and their energy spectra are sufficiently nice and the coupling is small enough, then you will produce new eigenstates, which are products. I think, to me, it sounds like a perfect analog, but yeah, perhaps it's a bit, yeah.
No, I think you have to refine this question, because when you talk about quantum integrability or chaos, you have to take a limit. So there is one limit, which is classical limit, and the answer is obviously yes, because in this limit, my quantum theory will become classical theory, right? Another limit we usually talk about is thermodynamic limit, but there you can remove word classical because there is no even classical version of KM theory. You can basically ask, is there a KM theory in thermodynamic limit? And forget about quantum.
Either classical or quantum. So what is the, probably, Peter, you said something. So they believe that KM, in classical case, they believe that KM and tori are there for any large number of particles, but this size becomes smaller and smaller, like exponentially small in n, thing like
That is what I understand from Unimovich.
your friend.
Yes. In a generic classical finite body system, there is a finite measure of non-ergodic initial states, which becomes smaller and smaller as particle number increases, probably exponentially.
Probably the same for quantum case. Yes. Yeah. You don't want to be recorded.
Said that there are finite volume that would be.
Right. Well, yeah, that's one analog, but not only. But, right. Yeah. Okay. Oh, yeah. That supplies my discussion. It's always there. Yeah.
But you see, there is an quantum system would make the same state. The almost all eigenstates satisfy exponentially fraction of them. Not exponentially.
That's it. It's not a big problem.
Well, but it is for me because he's sitting here.
That's common in this. Quantum case, if it is very exponentially small, it may be zero. You can count the number. Unlike the measure zero, it can be, if you compute and it's 0.001, it means zero. I think it's another difference.
Moment, I don't have a question. I have a short.
Yeah.
I think the question we debate in following quantum mechanically, the Hilbert space is larger if you classical limit. Mechanically, space quantum mechanics This is much richer than the classical one. Because the classical physics explores only a very small part of the Hilbert space, states with small entanglement. You know that the mechanical level, at least from the point of view of typicality, happens through typical states in the full Hilbert space, large entanglement. Classically, we do not see those states. I think the answer to the question quantum, we need to understand the concept. If the question we are asking sensitive to the full Hilbert space, live only in
The comment? Okay, anyway, we can comment to you later. We go slowly on, but it's already 35 minutes. Okay, so okay, this is the second of these miscellaneous, rather difficult technical question is this is raised by Keiji, Saito. Please be loud.
Since I see the quantum version of KM, I raised this question. For ETH, no-integrability is necessary, and usually we quantify no-integrability by random matrix and so on, level statistics. And no-integrability is well defined in classical systems, but in quantum case, it's a little bit more ambiguous to compare to the classical case. So the question is there is there any other way to define the no-integrability other than level statistics and so on?
That definition is a notoriously difficult question. So you said something during your talk. You want to add something?
I mean, that was one of the discussion. So one thing is you can look at observables and then they will satisfy the edge, but that depends. And another way is what I was arguing, that you can look at the entanglement entropy and you are dealing with that are quantum chaotic, like typical eigenstates of those systems. They have maximal entanglement. No different from random states. That would be a way.
You just said it's the way of knowing. It suggests that you have in mind that there is the definition somewhere. And these are just indications to, yeah. So I think Keiji's question is like, what is the definition? Oh, no? Probably I misunderstood. Do you think there's any the definition for this? And the way to see it is through level statistics or through entanglement entropy or through ETH. Or we can just look at these features and say, probably this was not a good question. Any other comments? Yes, Keiji has a.
By small systems, not only defined for many body systems,
Yeah,
also for few body systems, well defined.
Classically, you can define the notion of integrability for small systems, but your criterion should invoke the large system. Yeah. Right. So Peter is saying that in quantum mechanics, you are saying that you have to go to infinite volume limit to make distinction. So that's very different from quantum classical. Hero.
I'm not sure, but maybe we can use the computational complexity to define the integrability. For example, in the quantum case, maybe we can solve integrable models in polynomial time. But if we can take exponential time, of course everything is solvable because quantum mechanics is linear algebra. And in the classical case, we have some nonlinear dynamics. And I guess if the dynamics is non-integrable, even if it's a few body problem, maybe it takes exponential time. If we want some, almost exact solution, is sufficient precision. I'm not sure, but yeah.
That is interesting. Is that your idea or?
Maybe my friend's idea, but not my idea.
Not me. So in that case, then you're going to say that the integrability or not is undecidable, or?
Or it's sort of continuation of previous comment. I mean, one question is whether we want to define non-integrability or chaoticity. So these are two, in principle, different things. So I mean, non-integrability is just if we manage to define integrability, then non-integrability is everything that is not integrability. We closed. So we might discuss what quantum integrability is.
Okay.
But then separate question is how to define quantum chaoticity. And here, what we heard, I mean, in classical chaos, one way of defining is by complexity. Chaotic systems have, I don't know, positive dynamical entropies or scenario, something like that. That notion is quite robust. And try to define it for quantum systems. Problem is because usually such quantities are hard to evaluate. Are sort of nice on paper, but
Interesting.
A short comment on that, particularly on the definition, integrability, classical and quantum. I would say it's well defined. I mean, it's the notion of Lax equation of motion applies both classically and quantum mechanically. I just had this as the starting point of my construction today. It's just that for some reason I understand why people refuse this as a definition, and I believe it's because they want to see integrability as something that is decidable. So if I show you the Hamiltonian on the blackboard, they want to look at it and then within 1 second say it's integrable or not. But this is separate. If you are able to, I mean, definition can be a good definition even though you will not be able to tell whether the system at hand is integrable or not. I mean, for instance, you can have a definition, what is the, I don't know, Hamiltonian cycle, but then if I give you a graph and I tell you, can you get it? You will say, no, I can't, okay? So no one can, so how it works in integrability? You basically figure out what's the structure underneath, so some algebraic geometric principle, and normally it comes out, there is some equation related to that, and then finding solution to this equation will generate you an integrable model, namely families of integral models to be more precise. And then people classified all possible solutions of these equations, and this is how you get integrable models. So pretty much all the models that we discuss, which are integrals, I believe all, I don't know of any exception, come from there. And yeah, so, but then of course, if I give you some model, how can you say if this model can be embedded into this class? That's a separate question, and that's hard, and no one guarantees you that there exists an algorithm that will give you that, or even if it exists, that it should have good complexity. I think one should separate these two. It works for finite system as well, yeah. And it's not my definition, it's, I don't know if it was Lax the first who started it, but. No, using just that definition, no. Then you would have to do something what Marcos is doing. Look at the spectrum, and and then you have this heuristic, or how you would call them, I don't know. You have various probes, and then you believe in the Berry-Taber conjecture into Wigner. This is different, yeah. Correct. Because spectral statistics, you need infinitely many levels. Yeah. It does. I start with it is good. Finitely many degrees of freedom. There is this Lax structure underneath, and all the conservation laws and separation of variables, you name it, it all follows from there. And it's a good definition. It's just up to you if you like to accept it or not. Okay, and then as Marco said, non-integrability is.
Yes.
Yeah, but it's not, so it's, you want to construct eigenfunctions, and then there is no algorithmic procedure to do that. You have to suffer exponentially hard, right? Well, you have to diagonalize exponentially large matrix. Whereas in this case, because you have the LOC structure, it gives you, it's a gift to you. It gives you some structure which you can use. You have this separation of variables which you learn from classical systems, and you proceed and you solve the model at the end of the day, like I showed you today. So this you cannot do, right? And there is a difference. You cannot just say it's just the fact that I can diagonalize Hermitian matrices, right? So
yeah.
Can I just comment all this, because I agree that if we define integrability, then the problem is that we have to distinguish other cases in there is not only integrability and non-integrability. Because then, for example, if I can imagine some long-range model that can be solved in a mean-field way, then I think that I can give you such a model that you are unable to find the structure, but nevertheless I can solve it, and I will find some very special exceptional behavior, which is not a generic system.
Yeah, I think that's a good
so in
point.
that case, we have to.
So maybe solvability, which can be more broad term, can fall into various classes which go beyond integrability. That's in principle integrability, which gives you all this machinery for. It's essentially separation of variables what gives you, right? Classically and quantum mechanically. So this is basically coming from this Lax equation of motion. This is all I wanted to say. Now, if there is another case where you can integrate something, I don't know, a differential equation, the solution is special function, you solve it, right? So you integrate it, right? So it's integrable. Where is the Lax equation? Yeah. Then maybe this one should consider separately, denying this. But
okay, so this is heating up. I didn't expect. Keiji, this was a good question. Okay, so but now since we have banquet today, we cannot go on forever. So let me go to the next question, but I don't know. This is Peter's. But should we care about scars? Probably not. Or what? So that's Marcus. Is that your answer too, or?
I mean, first
yeah.
Will mean for like scars in quantum systems.
Yeah. So there are some examples, but. Is there any defender of the scar paradigm? So you want to say something, or no, you don't have to. You don't have to. If you want to defend the scar, you don't have to. If you want to say something, then.
There's times 4. Gives total time for amount behavior.
Yeah, but usually, well, okay, but this is a bit too detailed. Yeah. Yeah, but usually, even if the scar is there, you don't see that in thermalization scenario. Lisa, you want to say something? Mm-hmm.
Yeah, I think that I should care about scars. Yeah. The reason is very simple. Yeah, because scars, sometimes prevent thermalization. So yeah, a simple reason.
But in your example, scars did not.
Yeah. My example is not, but there are many examples. that scars prevent thermalization. So this is a phenomenon.
Why is that? I mean, scars are very rare, exponentially rare. Why is that? Why is it possible that they prevent thermalization?
Yeah.
It's too much detail. You can say it in a.
Yeah, but if we can fine-tune the initial state, then we can create the initial state that do not thermalize. I'm not sure whether scars are relevant for macroscopic world, but I think it's very important, for example, in the ultra-cold atom experiments.
Very good.
Maybe I can comment that they don't thermalize if you blindly look at the entire Hamiltonian. If you know that there are disconnected sectors and then you look at that sector, then it will perfect. It's not a black box.
This looks familiar. Okay. All right. So okay, we have from here. So this is a question about status of analytical rigorous results on thermalization or equilibration. So yeah, this is one thing. So we have lots of numerical evidence, which is very convincing, but this is related to this thing too. What are important findings that can be told to other physicists not in this community or mathematicians? So yeah, I worry about this too. This is not my question, but so what is the situation? Is there any?
On that, I think we need Tomas present, right?
Oh yeah.
He's really working on that question.
Okay, so
the way to address it is like has some rigorous.
Oh yes, that's great. So it thermalizes and.
Well, I mean they.
So yeah, if you are, so Thomas will be here next week. Yeah, I want to be here too, but.
Also a little bit more than that, right? I mean, systems where you have the interaction only in one point have been considered since, I don't know, since 25 years or so. So I mean, things like the spin boson model, but then made non-integrable, whatever it means, right? And these are typical systems where you can actually prove thermalization. So going back to, I don't know who started it, but Jacek Pile are names that are associated. So that's perhaps more in the mathematical physics community, but at least that exists. I don't.
We need to have a list of these things. Yeah, and you examine the data from the present point of view. Yeah, I think that should be done. Why don't you? Yeah. Well, we can. I think we can. Yeah, collaborate and make the list. Make the list of what can be told to outside. I mean, cooking up an example is really, really hard. That's really too hard. And we sort of believe that we do understand a lot. But when coming to answer this kind of question, it is really yes.
This converges for any time. So you can find the time evolution, it converges. And in particular, it's perturbative in this parameter, local. So this is a mathematical theorem, I don't remember. So now I understand because this is not consistent with what you're saying that it thermalizes. Because there are also other results showing that there is no thermalization when the perturbation is small and breaks integral.
Okay, so that's a very interesting point. So, certainly the very general way that you have phrased your claim now, I think that is not true. I understand we should not be too specific, but let me say why I think it's not true. If you just have something like, let's say, even free fermions, and you perturb them by some generic but small interaction just at the origin, right? I think that that will actually this will be a thermalizing in some sense, namely around the origin it will thermalize and disturbances will be carried away.
Unfortunately, this doesn't work. So there are evidence of the opposite. So
but there are also evidence for the positive. So we should just have a fist fight.
Works better. No, what I mean, if there is the evidence of the opposite is kind
okay. So
generally they don't. So
there's no contradiction. Why is there no contradiction? Huh?
So I'm saying no. If for in case for a generic, but completely generic local defect, the Hamiltonian it doesn't thermalize local in a large time around the defect. There is no, and there are also also paper by Alvise, Bastianello, showing that indeed it doesn't. And it's kind of clear also the picture because you can imagine that there is a scattering of particles, that there is a part of the scattering which is diffusive, but a part of the scattering is like
I don't.
You have always this kind of
Yeah, but I think that perhaps I should not monopolize the discussion. Just one thing, and then I shut up. So I think that perhaps the misunderstanding could be in what is meant here by thermalization, right? I mean, you have, and also perhaps from the starting point. So I'm really thinking specifically about free fermions, let's say in 3 dimensions. That's usually much better than in lower dimensions, right? And now I put something on around the origin, right? Something non-quadratic, okay, but small, okay. And then I want to see the thermalization in the sense of around the origin.
Yes, and this I think.
Okay, that's great. I would like to hear that. Yes, yes, thanks.
But that's very interesting. So probably we should learn about this thing, and we need references. I think I propose that I'm going to tell you my email at the end of the section. So if you have anything that you want to share, like the reference or your short comment to what is proved here, and then please just send me an email. Then I don't do lots of work. I just paste them and make a web page, and I tell Abhishek of the web page, and then he can tell everybody here about the existence of the web page. Yeah. Okay. So let's including this thing. So at the end of the this session, I will tell you my email address. So please send that to me, and then everybody will see the reference. Oh, it's already 1 hour. What shall we do, Abhishek? The final topic. Okay. Yeah. So we have to stop at some stage, but so probably we can stop. This is partially discussed in this, and so if you have anything, also if you want to propose something which we should tell to the general public other than like the lectures we had this time, please let me know through this email. And then everybody can share. And how do we teach statistical mechanics to students? Well, let's think about this. And probably many of you are teaching. So as Abhishek proposed, let's go to the final vague question. Did we learn anything about real thermalization? I don't know. Yeah, this is a vague question, so you can interpret in your own. Of course, did we learn anything about thermalization in cold atoms? Probably we did. No. But statistical mechanics is not about cold atoms only. So we are talking about, we are applying statistical mechanics to condensed matter physics, to compute susceptibility, conductivity, and we are using the notion of statistical mechanics. And so do all these shed some light on this kind of application of statistical? Peter, do you want to say something? Oh. Yeah. Oh, okay. Yeah. Go on.
I think yes, right? Because sort of a lot of the phenomena that perhaps were not yet fully presented in the conference, but will be there around about slow thermalization, let's say what people call stars, what I would call quasi many body localization, all these phenomena that probably, according to me at least, in the long run do not prevent thermalization. They are obstructions for very long time, and this is very interesting and experimentally very relevant. So yeah, so I don't see how we, I find it a very pessimist approach to say that we did not learn anything.
Very good. Anybody? Any other comments? Okay, if not, I think this is a very good time to stop, and it's exactly 1 hour. So thank you very much for joining this discussion session. And if you have any reference that you want to share or you should share with us, please send me an email.
You have this list on this.
Not really. So yeah, you should take the picture. Thanks. Thank you. It was fun.